Welcome. My name is David Charney. I am the Program Director and an instructor for the Ford Asset Program here at Parkland College in Champaign, Illinois. Thank you for taking the time to watch this presentation. My hope is that you are able to learn something about the history and evolution of electrified vehicles, along with some of their features and technologies, bringing that information back to your students. Why are we even talking about electric vehicles today? Good question. Some of the major automobile manufacturers such as General Motors and Ford Motor Company have committed to zero-emission vehicles by 2035. Ford claims they will have 40 to 50% of their global vehicle fleet at zero emissions by 2030. General Motors claims that their fleet will be zero emissions by 2035. So what does this mean for all of us? This means that ultimately we will all be driving fewer petrol engine vehicles and more all-electric vehicles in the very near future. Here's the basic evolution of what you'll find under the hood of these vehicles. First, you have a traditional petrol internal combustion engine, also known as ICE. You can see here you have your basic drivetrain components, an engine and a transmission needed to power the vehicle. Next, you will see under the hood of this hybrid vehicle, you will notice the addition of some orange cabling and a rather large box, which is known as the hybrid powertrain control module, that is the brains of the hybrid system. And then, as the evolution continues, you'll see under the hood of an all-electric vehicle absolutely nothing in the way of an engine. If you take a look here, it will help you visualize in a cutaway diagram of a basic internal combustion engine assembly and help you reference for the changes needed in the hybrid and electric vehicles. Transitioning from your basic petrol engine to a hybrid vehicle takes the addition of electric drive motors installed in the transmission, a high voltage battery pack, and a hybrid powertrain control module. With the addition of these components, you have the beginnings of a hybridized vehicle. Here is a cutaway of a Ford Fusion hybrid that shows you the high voltage battery pack mounted in the rear of the vehicle and an updated transmission which includes drive motors, as well as a hybrid powertrain control module which is mounted external to the transmission in the front of the vehicle. As we carry on through the evolution of electrified vehicles, you will see an all-electric Ford Machi, and for those Mustang enthusiasts out there, I will refrain from calling this a Mustang and simply call it a Ford Machi. Here is the cutaway of the internal components of a Machi. You will see starting from the left side of the picture and working toward the right, the front axle of the vehicle shows that it has its own electric drive motor unit as well as its own drive motor module, which is regulating power in and out of the motor. Next, you will see the large high voltage battery pack along the bottom of the vehicle. If you can visualize a skateboard where you have two front wheels and two back wheels with a board that connects the two, you can think of the battery pack as the board that connects the two sets of wheels and is truly a major structural component of the vehicle. And lastly, the rear axle in an all-wheel drive configuration has its own drive motor and control module and operates independently but in sync with the front drive motor. For reference, let's talk about the different types of hybrid configurations most commonly found in the auto market today: full hybrid electric, mild hybrid, and plug-in hybrid. Let's start with the full hybrid electric vehicles and list some of the features. Starting with full hybrid electric vehicles, otherwise known as FEVs, think about a Toyota Prius or a Chevy Tahoe. They have small electric drive motors in their transmissions. They have small battery packs between 200 and 300 volts, but not a significant amount of storage for energy. In electric-only mode, these vehicles will operate up to 25 miles per hour using no gasoline fuel. The battery of these vehicles is located either in the trunk or under the rear seat. They do not take up a lot of space and are recharged by regenerative braking as well as when the internal combustion engine is running. Next up is the mild hybrid. Think Honda Accord Hybrid. These vehicles have a small battery, generally 48 volts or less, that offer a small amount of electric motor assist. However, the benefits of the mild hybrid come in the form of the auto stop start feature, where when the car is stopped or idling, the combustion engine shuts off, yet all the creature comforts inside the car continue to run on the 48-volt battery system. This helps optimize fuel consumption. Along with this, the battery system does offer some electric assist or e-assist while driving, further improving fuel efficiency. Thirdly, we have the plug-in hybrid vehicle. These are very common. Think of a Ford Fusion, Toyota Prius plug-in, BMW plug-in, and etc. Many manufacturers offer this type of vehicle. These vehicles offer extended range by utilizing a larger capacity high voltage battery operating on 300 to 400 volts, along with an internal combustion engine offering a total range of 450 to 600 miles on a tank of gas. They also operate on electric-only mode for short distances of around 20 to 40 miles before using the ICE or being plugged in. To utilize the full hybridized features of these hybridized vehicles, you must plug the vehicle in to recharge the battery. Some recharging occurs through regenerative braking as well as the use of ICE. But due to the large capacity of the battery, ultimately it must be plugged in to fully charge the battery. Lastly, this brings us to the fully electrified battery electric vehicle, also known as BEV. BEV vehicles include vehicles such as Ford Machi, Chevy Bolt, Nissan Leaf, Tesla, Lucid, and Rivian. Many factors can affect the range of an EV battery. Range is very much dependent on how hot or cold it is outside. Too hot or too cold will reduce the efficiency and the range of the battery. Other factors that play into this: how much weight is the vehicle carrying? How many passengers is the vehicle carrying? How much weight is being towed? Also, how quickly a person accelerates while driving will affect range as well. Many BEVs offer a coaching system in the infotainment software that provides the driver with guidance on how to get the most range out of their battery during the drive cycle. This coaching also suggests how to properly decelerate your car to optimize regenerative braking. Next, we talk about the all-important question: how do I charge my all-electric vehicle? There are 3 levels of charging offered at this time. Each level has its own pros and cons. Let's start with level 1 charging. Level 1 is the most basic level of charging. Think of this as a glorified extension cord from your home outlet to the charge port of your vehicle. Level 1 is the slowest of all charging options, only offering about 6 miles of charge per hour. This means, for larger capacity batteries, you are looking at over 24 hours of charging needed to fill your battery at home. Level 1 chargers come standard with all plug-in hybrids and all electric vehicles. Next up, we have Level 2 charging. This is a significant upgrade from Level 1. This charging option provides anywhere from 20 to 60 miles of range per hour of charge. Level 2 chargers can be installed in your home. However, they generally require a certified electrician to install a dedicated 240-volt circuit required by the charging equipment. These chargers can commonly be found in the public space as well. You can find them in parking garages, hotels, grocery stores, and office buildings. The third type of chargers are the Level 3 DC fast chargers. Most people have heard of the Tesla superchargers, which are a Level 3 charging system. However, other manufacturers also make DC fast chargers. Level 3 chargers are the fastest available option to charge high-capacity EV batteries. Charging can take as little as 15 minutes to get half of your EV mileage range back. These systems are becoming more and more popular across the nation. Why this is so much faster at charging an EV vehicle? Well, that is because electricity has already been converted to direct current inside the charger, so it can be rapidly delivered to the car battery. These chargers are only commercially available and can be found in shopping center parking lots, grocery stores, and now some gas stations around the country. I added this picture as a point of reference. Charge receptacles do vary between manufacturers and level of charger. For example, Tesla makes their own non-universal charge receptacle, making it impossible at this point for a non-Tesla to use their charger. However, Tesla does provide an adapter that comes with the vehicle so they can charge at any non-Tesla charger. There are another two styles that you find most frequent. One is the J1772, which also offers level 1 and level 2 charging, and the other is a CCS combo, which can also use DC fast charging. Okay, let's recap the different levels of charging. This picture is shown as reference to the different charge receptacle outlets, voltage needs, and availability. Where can I charge? One of the biggest issues that I feel limits the sale of electric vehicles is the lack of charging locations. However, looking at the maps provided, you will see the wide availability of charging stations. The red dots are Tesla chargers, while the blue dots are Electrify America, which is a network of level 2 and level 3 chargers commercially available for a surcharge. Hopefully, as the charging infrastructure continues to expand, people's range anxiety will be diminished and EV sales will grow. Notably, vehicle mapping systems will route the driver to charging stations along their route and even tell the driver what kind of charger it is and how many spots are open for use in real time. Again, these chargers are found nationwide. Tesla and Electrify America offer the largest networks that I'm aware of. Rates at stations will vary depending on how many kilowatt hours the charger is capable of and how busy the stations tend to be. Idle fees also exist to keep chargers open and available. If someone leaves their car on a charger beyond the time it takes to become fully charged, a fee will be assessed per minute to encourage people to move along. As a reference, to fully charge a car will cost around $12 to $18. Let's take a look at emergency situations. What do I do if I miscalculate and run out of a charge? Well, that depends on where you are. So, you've ignored all the warnings that the car is low on charge. At this point, the vehicle will begin disabling features in an attempt to conserve charge. The AC or heat may be turned off, or the vehicle may encourage you to slow down to increase mileage. However, if you still couldn't get to a charger in time, there may be assistance in the form of a truck with a portable charger that can give you a boost. If that is not an option, your vehicle will need to be loaded on a flatbed tow truck and taken to the nearest charger. Note, BEVs cannot be pulled behind a traditional tow truck as the electric drive motors could become damaged. Let's take a look at hybrid and BEV vehicle maintenance. When maintaining hybrid and battery electric vehicles, there are some differences between the two. Remembering that hybrid vehicles utilize an internal combustion engine, hybrid vehicles require very similar maintenance to non-hybrid vehicles. Oil changes, tire rotations, engine air filters, coolant flushes, just to name a few, are still required. With a battery electric vehicle, maintenance is significantly reduced. Let's take a look at what maintenance is required on a BEV. Tires and cabin air filters are really the only wearable maintenance items on a battery electric vehicle. The brakes are rarely used due to the regenerative braking by the electric drive motors. There is no transmission, so you don't have to worry about flushing it, and there's no power steering fluid since it's electric, and there are no belts. So maintenance on these vehicles is very light. Now it's time to talk about safety and technology on electrified vehicles. Tesla Autopilot, General Motors Super Cruise, Ford Copilot 360, and Rivian Driver Plus. These are all manufacturer-specific driver assist systems. Let's take a closer look at what these driver assist systems are capable of. Each manufacturer offers some level of the following: lane keep assist, adaptive cruise control, self-driving, collision avoidance, evasive steering assist, and parking assist. There may be other features depending on the manufacturer and trim level purchased, but most cars these days have some form of an advanced driver assist system, also known as ADAS. But more specifically, we are talking about this now and how it relates to battery electric vehicles and the evolution of these programs into autonomous driving capability. For example, Tesla and their autopilot full self-driving feature. Let's take a look at how these systems work. ADAS works by using cameras located outside and inside the car, GPS, sonar, radar, LiDAR, and a lot of cellular data. Vehicles with some level of autonomy use cameras to watch the driver, making sure the driver is alert and attentive to the road. If the camera senses the driver is not alert, the vehicle will attempt to capture the attention using visual and tactile and auditory alert systems. If the driver fails to respond, the vehicle will turn the hazards on, slow down, and pull off to the side of the road. Some systems are capable of alerting emergency personnel. This brings us to the different levels of autonomous driving. Level 0, no assist. Maybe some alerts that let the driver know that they're veering out of their lane. Single assist, basic adaptive cruise control. Level 2, advanced driver assist system. Speed, steering, and braking are controlled by the vehicle. Level 3, takes control of all critical safety features. No input from the driver needed in an emergency. Level 4, high automation. No driver input necessary. The vehicle is in control. Level 5, full automation. No driver necessary. For those of you familiar with Tesla's advanced autopilot, this will make sense to you. For others, I encourage you to do research on how impressive and seamless Tesla's autopilot system operates. However, as advanced as it is, the system is still considered a level 2 autonomous vehicle, which goes to show you how much the future holds for advancement of autonomous driving. Autonomous limitations. The U.S. and state governments are currently working on legislation that affect legality of autonomous driving. There are a lot of factors to consider for just handing the keys over to the car. Examples. Who will be at fault in an accident? Can you still be charged with a DUI if the car is the one driving? Is being a licensed driver even necessary anymore? Another factor to consider are the ethical decisions that a car will need to make. Which choice does a car make, and how do we program the cars to make such a choice? Do we save the driver and kill the pedestrian? Or do we swerve and potentially kill the driver by hitting a tree but save the pedestrian? Or do we trust artificial intelligence to make those decisions? As you can see, there are a lot of factors and logistics to consider. Another limitation is the development of 5G networks throughout the nation, since they are important to proper functioning of autonomous vehicles. The cars are constantly uploading and downloading information while also communicating with other cars around them. They are receiving information about roads, weather, location, and traffic constantly. They are using all of this information to calculate accurate locations in real time and make split-second decisions. Until 5G infrastructure is widely implemented, we will be limited in our autonomous abilities. I borrowed this from Intel, but this shows the staggering amount of data that autonomous vehicles require. As reference, a person uses about 4 gigabytes of data a day, while an autonomous car will eat up 1,000 times that much in a single day. Looking at the picture, you can see how much data each system is using per second. This is why a solid cellular infrastructure is so important. In closing, the idea of being able to read a book while driving down the interstate in a fully electrified autonomous vehicle may soon be a reality. I think in the current generation of 16-year-old drivers, they are going to have the opportunity to learn how to drive behind the wheel of some level of autonomy. Think about the children whose parents own a Tesla. Those young drivers are getting a completely different driving experience than what us adults ever experienced. What does this mean for driver's ed in the future? We probably don't have an answer to that yet, but it's something to consider. On the other hand, I'm very excited and feel more comfortable than ever with my child behind the wheel of a vehicle equipped with advanced driver assist systems, helping to protect them. Autonomous vehicles offer a level of safety that we've never been able to reach before, even though many people haven't learned to trust the idea yet. However, I think electrified vehicles are the wave of the future regardless if we go full autonomous or not, and we will continue to see more electric vehicles on the road as that technology continues to develop.